it's covered in the exam, so let's try and finish it this morning, and then tomorrow we'll summarise, have a quiz and practice for the midterm and discuss the midterm. So now what we know is when we want to communicate data, we send signals across some link. That signal, as we transmit it, may get weaker, it attenuates, there may be noise, and as a result the signal at the receiver is different from what was originally transmitted. And if it's too different, then the receiver will make some mistake in terms of thinking what the data was. If we focus on digital data, that is, we're transmitting bits as the data. The signals may be digital or analog, but if we look at digital data, if we transmit our data as some signal and there's some noise in the communication system, then the problem or the result of that may be that there are bit errors. We transmit bits 101, we receive a signal and the receiver thinks it's 111. There's a bit error in there. We need to look in this topic at techniques for detecting those errors and start to look at techniques for correcting those errors. So first we want to know whether an error occurs or not, and second we want to know if an error does occur, can we fix it? Can we get the original data? And that's what we'll look at in this topic. Bit errors, so if we're looking at digital data being sent, then a bit error is when the bit that is transmitted or the bit that is received is different from the bit that was transmitted. I transmit a signal representing bit 1, the receiver receives that signal, and because of imperfections or impairments, it thinks that signal represents bit 0. The wrong bit has been received. So we want to avoid bit errors, but because there's noise and attenuation and different impairments in the system, in practice they may occur. They may occur as single bit errors, and they're the most likely. That is, there's some random noise in the system from the background, from other transmitters. Then we send a sequence of bits, 100 bits. One of those bits may be received in error, the other 99 bits are received correctly. So that's a case of a single bit error. Or we may have a burst of errors. That is, there may be a certain event, for example an impulse of noise, some electrical fault that causes a large impulse of noise for some period of time, and as a result we transmit 100 bits, and a group of those 100 bits are impacted by that impulse of noise and are received in error. So we have a burst of, say, 20 bits received in error. Single bit errors can occur randomly in communication system. That is, because there's always some noise in the system, and generally we consider that noise to be random, then depending on the magnitude of that noise and the magnitude of the transmitted signal, we may have single bit errors or extended to double bit, triple bit errors. Everyone's ready for the quiz? Thank you. You can have a quiz on next lecture. This is the quiz for IT, which is after this. So you may have single bit errors. And in fact, it's not so precise when we say single bit errors. Okay, there could be 2 bits in error. When we talk about a burst of errors, there's usually a large group of bits in error. Burst errors, the impact of impulse noise or fading, some impairments, is larger at higher data rates. That is, if we have some noise, which is quite small, and there's always some noise in our communication system, and then there's a large impulse of noise. Some electrical fault or some problem in the system means for some period of time there's a large amount of noise. Then all of the bits that are transmitted during this time are going to be impacted by this impulse of noise. So if we're transmitting bits as some digital signal, then all the bits transmitted in this period of time will be impacted by this noise. So the number of bits that can be potentially in error in this case is this 1, 2, 3, possibly 4 bits could be in error, depending on their value and the magnitude of the noise. If we transmit at a higher data rate, this is noise.
And the upper one too.
This is time. So time is going this direction. So if we think of noise as some random variations, but in some cases maybe that there's an impulse of noise due to some fault, some other transmitter transmitting. So the noise is quite low. It's going up and down randomly.
And the upper one.
And then there's some impulse of noise. That is, the magnitude of the noise increases, and then just for some period of time, and then it goes down again.
Online is noise.
This is noise. Yeah. This is an example digital signal representing some data. In this example, this impulse of noise could impact upon the bits in this time period, about 4 bits. But if we were transmitting at a faster data rate, if we transmitted at double the data rate, then our signal would be not very accurate. What I'm drawing here is, okay, here's one signal element, or let's say a signal element representing 1 bit. And in this case, within that same time, we have 2 signal elements representing 2 bits. So the data rate in this case is double this one. We're sending twice as fast. In this case, the same amount of noise, or same duration of noise, would impact on approximately 8 bits. So double, if we have double the data rate in the same period of time, double the number of bits. The point is that if we have some impulse of noise or some event of noise that may cause errors, the faster we're sending, the more bits that may be in error. So there's another trade-off that we need to deal with. The faster we send, we may get more chances of errors. Now, whether it's an error or not depends on exactly what the value of that noise is and what was transmitted. But the chance of errors doubles if we're sending twice the speed. So we need to deal with errors somehow. We need to be able to detect errors and, where possible, correct them. Another example. Some other signal was sent, the receiver receives the signal and decodes the received signal and gets this sequence of bits. So this is the sequence of bits received by the receiver. Are there any errors in this sequence? Anyone? Are there any errors in this sequence? Not yet? The answer is I don't know, which is correct. You don't know, the receiver doesn't know. Remember, if the transmitter sends a sequence of bits, the receiver doesn't know what the original sequence was. All the receiver knows is the signal received, and as a result, the bits received. So the question arises, we receive this sequence of bits, now we need to determine, are there any errors in there? We need to try to detect if there are any errors in there. We cannot do it by simply looking at it because we don't know what the expected sequence of bits were. So we need to perform some error detection. And of course, if we detect an error, we would like to fix it. We would like to get the original data received correctly. So we need also error correction. So let's go through those techniques. Error detection first. So the idea with error detection is to, with the data that's being sent, include some extra information, an error detecting code. We transmit the original data plus some extra bits which is going to be used to help the receiver to detect if there's errors or not. It's called an error detecting code in general. This diagram shows the general process. The transmitter here and the receiver here. The transmitter has some data, k bits of data. So we work in blocks of k bits at a time. We have k bits to transmit. What we do is we apply some function on that data, and we'll give you 2 examples of those functions, and there are many. Apply some function on that data and get some result, E, and take the k bits of data and these E bits, the number of bits is n minus k, and attach them and transmit all of them across our link. So we don't just transmit the data, we transmit the data plus the error detecting code, where the error detecting code is calculated from the data. So we have k bits of data, n minus k bits of an error detecting code, k plus n minus k, a total of n bits here are transmitted across our link. So we transmit them across the link. There may be errors in our link. That is, we transmit a sequence of bits. What's received may be or may not be the same. We don't know at the receiver. So the receiver receives a sequence of bits. It knows the function that was applied here. It knows the error detection scheme that was used by the transmitter. So it knows the first k bits are the received data. The next n minus k bits are the error detecting code. What it does, it takes the received data, applies the same function as the transmitter did, and gets some result, and compares the calculated result with the result received. If they are the same, it assumes that there are no errors. If they are different, it assumes there are errors. In error detection at this stage, all we're trying to determine, simple yes-no answer, are there any errors in the data we received? We don't necessarily care where the errors are. We want to know, are there errors or not? So the idea is to choose a function such that if any of those bits have been altered, we transmit a sequence of bits. If the bits received are different from what is transmitted, then if we apply this same function, then the result of this will be different from what's received here. So we need to have such a function such that if some of the bits have changed, then applying the function will give a different result than what was received. Let's go through an example to illustrate this in some more detail. There are many different approaches for error detection. We'll go through a very simple one, which is parity check. And you may have covered that you may have seen it in computer hardware courses. Simple single bit odd parity check. We take a block of data, k bits. In an odd parity check, we add one more bit, which is our error detecting code, such that of the n bits, there are an odd number of ones. We transmit those n bits. The receiver receives a sequence of n bits, counts the number of ones. If there are odd number of ones, it assumes it's correct. If there are an even number of ones, it assumes incorrect. That is, The transmitter always transmits a sequence with an odd number of ones. Therefore, the receiver should expect to receive a sequence with an odd number of ones. If it receives a sequence with an even number of ones, it assumes that there's an error. So that's the example of an error detection scheme, maybe one of the simplest we can see, and is used in a number of applications or a number of systems, especially where simplicity is required. So let's go through an example to show that one. We want to send some data, and in this case the data is a character. I want to send a message, English alphabet. Then what I'm going to do is the original data, some letters, I'll encode into bits. In this case we'll use an ASCII table to map the English letter to a 7-bit number, and that will be the data that I want to transmit. And if we're using an odd parity check, we'll see what happens. If we went back to, I think you have it in front of you, the ASCII tables in one of our original lectures or one of our previous lectures, there's the ASCII table which gives us the mapping of all the characters, the English characters and other keyboard characters, to binary values. So this question says assume the character S. I don't have the answer for S. I do have the answer for another character. Let's change it to Q. Q, instead of the character S, can be is represented from the ASCII table as a 7-bit number. This is a 7-bit number representing the letter Q from the ASCII table. You need to look that up to find what that value is. You don't have to remember. That's our data that we want to send. So at the transmitter, well, let's say the data to transmit, TX, transmit, is this 7 bits. We're using, any questions so far? Is that correct? You can see on one of your lecture notes the ASCII table.
Does it have to be, oh, this one.
First column, lowercase q. So this is the data we want to send. We're going to use an odd single-bit parity check, and we're going to include the parity bit at the start of the data. It needs to be defined whether you include it at the start or at the end. In this case, we're going to include it at the start. So what we do is we take our data and we add a parity bit such that when we combine them, if we call the combined block of bits and the parity bit a frame, and we'll transmit that frame. This is 7 bits. In our notation, that's the value of K. In our diagram that showed the general procedure for error detection, we said we have K bits of data. In this example, K is 7. We're going to have a single bit parity check. So we're going to transmit a sequence of n bits, or 8 bits in this case. What's our parity bit?
1.
1. Why is it 1?
Because we need the frame to be contained on the row.
Because we need the frame, that is the 8 bits, needs to contain an odd number of ones. So we've currently got an even number of ones, so we add another one and we'll have an odd number of ones. So I'll just mark it as red, that's the parity bit. We're going to add at the start. So what's known by the transmitter and must also be known by the receiver is that we're using odd parity, that we have expect an odd number of ones, that we have a single bit parity check and it's included at the start of the data, and that we're using 7 bits. So we have 1, 2, 3, 4, 5 ones, our odd number of ones. This is what's transmitted across our link. So let's look what the receiver does. So it's quite simple. If we have an even number of ones in our data, add a 1. If we have an odd number of ones, add a 0. We transmit this frame across our link. Now there may be errors in our link, and maybe there may not be. Let's consider first case, what if there are no errors? That is, the receive frame is identical to what was transmitted. So our link is from, we transmit it and it arrives at our receiver computer here. The receiver doesn't know what was transmitted, it only knows the signal it's received and it codes to get this sequence of 8 bits. So now it does its check. Okay, it's quite simple. We expect an odd number of ones in the frame that we receive. The transmitter always transmits an odd number of ones. Count the number of ones, we have 5 ones, that's odd, no error. That is, we assume that there's no error in the data received. And therefore we remove the parity bit and the received data is simply this 7-bit sequence of 7 bits. Because the received frame had an odd number of ones, the receiver makes an assumption that there are no bit errors and therefore accepts the data in that frame. So a very simple scheme. The outcome is either there are errors, or the receiver makes an assumption either there are errors or there are not errors. In this case, because the odd number of ones assumes no errors. That's easy. And of course, in this case, we get the correct result. We transmitted this data, we received that we transmitted the data here, we've received the same sequence of bits. The data received is the same. There were no errors in our link, and the receiver made the correct assumption that there are no errors. So all the receiver does is count the number of ones in the received frame. That was easy. Try again. Let's say there is a 1-bit error. From the frame transmitted, the frame received is this. One of the bits is in error. In this case, I know it's this. The receiver doesn't know it's this bit. It just knows it's received a sequence of bits. So it applies the same check. Count a number of ones. 1, 2, 3, 4, 5, 6. Even number of ones. Error detected. No data received. Once we detect an error, we'll need some other mechanism to try to correct that. So that's it. The receiver now has detected the error. Try it yourself, where the last 2 bits are in error. Quickly try what happens. We've got the transmitter frame and the last 2 bits are different from what were transmitted. What does the receiver do? That is, these two bits are inverted at the receiver. What's the outcome?
1 1 1 1 0 0 1 0.
What's the outcome? Okay, so let's the last two bits in error, so we receive 410010.
But it is actually error, but it is still
Okay, easy.
ตัวหลัง7ตัวมันก็จะเป็น0
ก็
0
มันที่มันเป็น
1
อยู่แล้วดังนั้นถ้า data ตอนแรกมาเป็น
0 0 1
มันก็
0
รีบ
Yep. Hang on. Any questions? No? Okay. Okay.
So we get R.
Let's have a look, see what we get in this case. Some people have worked it out. This is what's received if the last two bits are in error. We apply the normal check. Count the number of ones, 5 ones, odd. Assume it's okay. If we have an odd number of ones, the receiver makes a decision. No errors have been detected. Therefore, the received data, take these 7 bits, and we have a problem. The transmitted data was 111110001, representing the letter Q. The received data that the receiver thinks was transmitted is 1110010. And it doesn't know any better. That is, it assumes this is correct when we know that it's not correct. So here, the error detection scheme did not work. There were 2-bit errors, and the receiver did not detect those errors. As a result, the data that the receiver has is incorrect. That's an outcome that we don't want to happen. Yep.
We add one as a parity bit because this one we include the parity bit too, right?
We add a parity bit such that the total number of ones is even in this with odd parity. With even parity, it's the opposite. The total number of ones should be even. With odd parity, the total number of ones should be odd. With even parity, the total number of ones should be even.
So we add one.
Add one.
If they have odd number or even.
We add a bit such that the total number of ones are odd.
Okay, so if they have three number of 1, like 1
Here.
1 0 0 0 0, then what we have? What parity?
Bit 0. So we've only got choice between a bit 0 and a bit 1. If what was transmitted was, like you said, this, then the parity bit would be 0. And we'd get, this is an odd parity check. In this case, we're using just a single bit parity. Single bit odd parity check. It can be different. You add a 1, you've only got a choice between a bit 1 and a bit 0, and only a single bit, such that the resulting sequence of 8 bits has an odd number of ones. And in this example, I've assumed to add the parity bit at the start. Another case, I could add it at the end. As long as the transmitter and receiver know what each other are doing. That is, both the transmitter and receiver need to know we have an odd parity check, single bit, and we're adding the bit at the start, and that we're using 7 bits of data. So they both need to know those details prior to this happening. So we saw now that we had 2 bits in error. The receiver did not detect those errors and therefore receives the data, and that's an unsuccessful outcome of this error detection scheme. We didn't detect the actual errors. That's not good. So this single bit parity check is not very useful in a number of cases. What are those cases where it doesn't work? When does the single bit parity check not work?
Even number of bits.
When there are an even number of bit errors. In that example, there were 2 bit errors. The errors were not detected. In the previous example, there was 1 bit error. The error was detected. With 3 bit errors, it will be detected. 4 bit errors not. So in fact, the single bit parity check is not very useful if we have more than 1 bit single bit errors, because it will not detect the errors. But it's a very simple scheme, and if we expect, when we transmit our data, if we send 8 bits, if the chance of an error is very, very low, then in most cases we'll only have single bit errors. The chance of having 2 bits in error in this sequence is very, very low. So it may detect many cases, but it will not detect the cases if we have 2 bits in error. So in fact you can measure or you can compare different error detection schemes based on the ability to detect. First, note that if we assume that errors are random, we have a large sequence of bits to transmit, and there's 1 bit every 1,000 bits transmitted in error. 1 in 1,000 are in error, but it's random. We don't know. Some cases it's the first bit, sometimes it's the 500th bit, sometimes the 673rd bit. It's random. Then the chance of, in this sequence of 8 bits, 1 bit in error is quite small. The chance that in this sequence of 8 bits, 2 bits in error is very, very small. So the chance of getting 2-bit errors is much lower than the chance of getting single-bit errors. And similar, the chance of getting 3 bits out of these 8 in error is very, 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 very small. So the chance of more bit errors in our frame decreases as the number of bit errors increases. So normally we'd like to be able to detect single bit errors. Detecting double bit errors, it would be nice, but in some cases it's not so important because double bit errors do not happen much. But still, parity check is very simple, but does not work with more than, or it does not work when we have an even number of errors. We'll see in detail another case of error detection when we look at error correction, but another algorithm, and you've heard of it, is CRC, the cyclic redundancy check. It's commonly used, and it's stronger than the parity check in that it can detect more errors than the parity check. We're not going to go through how the algorithm works. There's some description or treatment in the textbook. We don't have time to go through that. But it's better than the parity check, or more powerful in that it can detect more errors by sending the same sequence of bits. And it's used in wired LANs, Ethernet, some data link protocols, things like communications between hard drives, and many other systems. So the CRC check is a commonly used error detection algorithm. Much more complex, but much better at detecting errors. Another thing to note is these values. In general, we have k bits of data and n minus k bit error detecting code, and as a result we transmit an n-bit frame. As if you add these two together you get n. In general, if the larger the error detecting code compared to the data, the better we can detect errors. So the ratio of the error detecting code to the total frame size is usually used as a measure of how good the error detection or an error detection scheme can be. Because if we have more bits in our error detecting code, we can, for example, if we have a 2-bit parity check with the same 7 bits, we may be able to detect more errors, detect cases which would not be detected with a single-bit parity check. That will become evident when we look at the third approach in error correction. But in general, increasing the length of the error detecting code increases the capabilities to detect errors. So that's the advantage of increasing the length. What's the disadvantage? The longer the frame that we need to transmit. I have a data rate of my link of 8 megabits per second. So in this case, I have 8 megabit per second link from transmitter to receiver. What's my throughput? If there are no errors, what's my throughput? I've got an 8 megabit per second link using my single bit parity check in this example. If there were no errors on our link, what would my throughput be? What would the throughput be? So keep going. 7 over 8 times by 8 would be 7 megabits per second. Why? Yeah, we have 7 bits of real data, 1 bit of error detecting code, which is not the real data that we're communicating. So in fact, we transmit 8 bits, and only 7 of those 8 are real data. So if we're sending at 8 million bits per second, only 7 out of every 8 bits are real data. So the rate at which we receive that real data is 7 over 8 times by 8, which would be 7 megabits per second. That is 7 out of every 8 is the real data, 1 out of every 8 is the error detecting code. So the larger we make the error detecting code compared to the data, the lower the throughput. That is, we have more overhead. We're transmitting more bits which are not real data. So the negative part of increasing the length of the error detecting code, the disadvantage, is lowers the throughput. The advantage, it can detect more errors. So there's a trade-off that needs to be considered.
We can call it overhead.
Yes. If this is our data, everything that we transmit which is not data, we can classify as overhead. Yeah. In this case, we have 1 bit overhead every 8 bits we send. So error detection, we've just seen one simple example, the parity check. There are other algorithms. For error detection, the receiver knows if there are errors or not, but in some cases it doesn't work. So in fact, we could summarize with error detection. Three cases. If we transmit our data, and if there are no errors in the link, then, and the receiver will receive the frame and know that there are no errors in the link and gets the correct data. So that's a successful outcome. We transmit, no errors, we receive the exact same data as what was transmitted. So that's what we'd like our error detection algorithm to provide as an outcome. But in some cases, if we transmit data and there are errors in the link, if our receiver detects them, then that's a good outcome as well. We cannot avoid errors in some cases in the link, so if we can detect them, that's good. We'd like an error detection algorithm that would detect those errors. In some cases, like we saw, we may transmit data. The receiver cannot detect those errors. We'd say it misses the errors. Not good. We want to minimize the chance of that happening. So 3 different outcomes there. We'd like to choose an algorithm such that this is minimized. In practice, that may always happen. We just like to reduce the chance of it happening. Of course, what do we do once an error is detected? If an error is detected, what do we do? How do we correct it? Ask the transmitter to send again. If the receiver detects an error, it could send a special message back saying, please transmit those 8 bits again. I had an error. And it will transmit it again. And hopefully in this case there are no bit errors, hopefully there are no bit errors. Because bit errors are random, then if we transmit 8 bits and there's an error, transmit the same 8 bits again, hopefully the second time there'll be no error. If there are, try again and try again. Retransmission. So we'd like to be able to correct errors. And that's the first case there. So there are 2 basic cases for error correction. One's that we just went through, retransmit. If you detect an error, ask the transmitter to send again, to retransmit the data. And that's a very common approach, and we're going to spend several weeks looking at what's called data link control protocols that do that for us, but after the midterm. That approach has some problems in that in some cases when there are many errors, it can introduce a large overhead, because all these retransmissions introduce overhead. To send just 7 bits of data, we need to retransmit many times. That can be a problem. So there's an alternative, and that's what we'll go through today. It's called forward error correction. The idea is to not have to ask the transmitter to send again. The idea is that the transmitter includes extra information in what they originally transmit, such that when the receiver receives it and detects an error, the receiver can also correct that error at that point in time. So, forward error correction. Rather than having retransmissions, just include enough information in what's transmitted the first time to be able to correct an error if it actually exists or is detected. Now we'll look at one example of an error correction scheme. Again, there are others. And at the end we'll come and compare them. Or look at metrics for comparing them. What we do, and we'll use the example to describe this in detail, is we take our original k bits of data that we want to send, we encode that. We use what's called a forward error correction encoder. Instead of sending those k bits of data, we send a code word which represents that data. Another sequence of bits to represent that data. So there's some encoding that maps the input data to a code word. We transmit that code word, where the code word is n bits in length. Transmit that. There may be bit errors. We receive some code word, use the decoder, and the output of the decoder is either the data received has no errors. That's the first output. Everything's okay, and we receive the data. There are errors, so the decoder may detect errors. So it's also error detection. And it may also correct those errors. So we may receive the correct data, or we may get an outcome that we detect errors and we cannot correct them. We'll see those different cases. But the important thing here is that we have the data to transmit and we encode that into a code word. Whereas in our error detection, our parity bit, we took the data to transmit, we simply added some error detecting code. In this case, we're going to take the data and transmit something different, a code word. We'll use an example to illustrate this process in more detail. This example we're going to use as the encoder, decoder, we're going to use the concept of a Hamming distance. A Hamming distance is a measure of how close two sequences of bits are. So take this simple example. If we have two sequences of bits, V1 is 0, 1, 1, 0, 1, 1, and another sequence of bits, V2, 1, 1, 0, 0, 0, 1. So two 5-bit sequences. The Hamming distance between those two sequences is the count of bits that differ. Look at the first bits. Are they the same? No, they differ. So we have one bit is different. These two bits are the same. These two are different. So we have two bits that are different. Same, different, so we have 3 bits different, and the same. The Hamming distance between V1 and V2 is 3. So it's a concept for determining how different two sequences of bits are. It's not just used in error correction, it's a general concept. We'll use that in our example. Quickly, what's the answer? The distance between these two is 0. And another easy one. The distance between these two sequences is 0. They are the same. The distance of 0 means that the sequences are the same. In this case, we have a 4-bit sequence. If the distance is 4, then all bits are different. So the larger the Hamming distance, the more the two sequences are different. A distance of 1 means only 1 bit differs of the entire sequence. And so we will use this concept at our receiver. So in our example, we've got our transmitter we have an encoder, and in this example we're going to have 2 bits of data that we want to transmit, k equals 2, and we're going to map it to a 5-bit code word. So n equals 5, and transmit the code word. And this is the mapping in this example. That is, whenever we have this 2 bits to transmit, we're in fact going to have the code word of all zeros and the other 4 values. This mapping is just chosen for this example. It could be a different mapping, but it must be known by both the transmitter and receiver. So the transmitter knows this table and the receiver knows this table. That's our encoder, and the receiver has it as the decoder. That is, when the receiver receives a code word, it will get the original data back, decode. So what the transmitter does is simple. If we have some data to transmit, transmit the corresponding code word. On the next, I think, 3 slides, we have an example, and we'll go through them to illustrate this. The selection of these code words, there are some good ways to select them, but in this case, I've just chosen them just for this example. It could be a different selection, but in fact there are some optimal ways to select the code words. We'll talk about later. Our transmitter has some data to send. As an example, the bit 01. So all the transmitter does is determines the corresponding code word, looks in the table, so this is the encoder, input 01, code word 00111, and transmits that code word across our link. So the receiver receives a sequence of 5 bits. First case, let's say there are no bit errors across the link. So what the receiver receives is identical to what was transmitted. So in the first example, which is on the next slide, we transmit these 5 bits. There are no bit errors on the link, therefore we will receive the exact same 5 bits. What the receiver does when it receives the code word is that it checks whether it's a valid code word. There are 4 valid code words, the 4 in our table. And how many invalid code words?
0.
How many invalid code words? Not 0. And your high school mathematics will tell you the answer of that is?
Ask Ittipon of mathematics. Ask what is.
So our 4 valid code words are simply these 4 values in the table. You don't have to write them down, I just list them just for convenience here. And because we've got a 5-bit code word, there are 32 possible values, 2 to the power 5. 4 of them are valid, the other 28 would be invalid. For example, 0001. That's not one of the valid ones, and 27 others. There are 4 valid and 28 invalid code words. Simply the invalid code words are the values, the 5-bit values which are not these 4 valid code words. The transmitter always transmits a valid code word. It always transmits one of these 4. Therefore, the receiver expects to receive one of those 4. So in our example, the receiver received a code word. The first thing the receiver does is checks whether it's valid. So it checks this against the 4 values. Is it valid? Yes, this matches this value. So it's a valid code word. If the received code word is valid, then the receiver assumes that there are no errors and does the decoding and gets the original data. And the decoding is simple. Take the code word and get the original data from the table. Receive code word 00111, it's valid, therefore look up in the table and our received data is 01. Of course, this is a simple case because there were no bit errors. Everything was perfect. But we have some overhead, so we'll calculate the impact of that later. That's a good point. We transmitted 01 as the data, and the data received is 01. So everything's correct in this case. We've received the correct data. Let's try again. We'll leave this here. Same data transmitted, same code word transmitted, and there's one bit error. Let's say the middle bit. Doesn't matter which bit. Well, it does, just for my example. Doesn't have the answers for just one case. The middle bit is in error. That is, this is what is transmitted. The receiver receives these 5 bits. We see that the third bit is different from what was transmitted. As an aside, when I talk about the first bit, I mean the leftmost bit. Just for simplicity, the leftmost bit is the first bit, the rightmost bit is the last bit. Transmitted, received. The receiver does the check. Is this a valid code word?
No.
We compare it to our 4 valid values in the table, not valid. Because it's invalid, immediately we've detected an error. So in fact, this is error detection. Why is it an error? Because the transmitter only transmits one of these 4. If we receive something different, then something's gone wrong. At least one of the bits has changed. So we've detected an error. Let's try and fix it. So to try to correct that error, we take our received code word and see how close it is to the 4 valid code words. And the measure of closeness is our Hamming distance. So what's the Hamming distance between our received code word and the first valid code word? The D, I'm just going to list the values here. That is, I'm comparing this to this valid code word. The distance is 2. The received code word to the second valid. Third one. 3. Let's check. First bits are different, that's 1. The second bits are different, that's 2. Third bits are the same. The fourth bits are different, that's 3. And the last bit are the same, so there are 3 bits different. Therefore the Hamming distance is 3. And the last one? 4 bits are different. So first we compare the received code word to the 4 valid code words, calculating the Hamming distance. And now we make an assumption. If one of the valid code words is minimum, and that minimum is unique, and that is the case here, this is the closest. It has a minimum Hamming distance, or the minimum Hamming distance is 1. Only one valid code word has that minimum Hamming distance. Therefore we assume, this is the received code word, we assume this one was transmitted. That is, if there's an error, we would expect it's most likely there's a single bit error. It's less likely there are 2 bits in error, and even less likely that there are 3 bits in error, and very, very, very unlikely that there are 5 bits in error. So the approach of the receiver is, okay, we know there's an error detected, so let's choose the valid code word which is closest to what we received, assuming that the number of bit errors is low. So we assume that the received code word, or the transmitted code word, at the receiver, we make an assumption that the transmitted code word must have been 00111, because that has a minimum Hamming distance of 1 to our received code word. And now we decode. Take this, look up the table, data 01. We've corrected our error. The transmitter had the data 01. It transmitted a code word. There was a bit error on our link, so there was an error. The receiver detected that error because the code word received was invalid, and then corrected that error, because eventually the received data 01 is what the receiver thinks the data was, matches what the transmitter knows the data was. So even though there was an error, we've got the correct data received. So the process, after an error was detected, calculate the Hamming distance to each of the valid code words. If one of them, and only one of them, is the minimum, then assume the corresponding valid code word is the one that was transmitted, and then decode from our table.
Yep. Which one is more popular? I mean, like, which one usually do with our computer? It's with the forward one or the retransmit?
The retransmission is very common in a number of protocols. So your computer, when you're browsing the internet, things like TCP will use retransmission. Forward error correction is commonly used on links, especially links where bit errors are more likely. Wireless links especially. Mobile phones, we have a wireless link, forward error correction is used. And in many cases, one protocol would use forward error correction at one layer, and at a different layer they may use retransmission. So in fact both are used at the same time. We've covered that example. We just covered the second example where the third bit transmitted is in error. Oh, do we have another one? Where? Example 3. Do that one. Try it now. Same transmitted data and code word. Look what happens at the receiver. So the first and fourth bit are in error. I'll just go back. We're still using the same encoder and decoder. Solve this problem. Example 3. What's the receiver do? Error, confused. Okay, that's about right. That is, it's detected, but we cannot correct it. Let's see. Received code word, what do we have? First and fourth bits. Valid? Is it a valid code word? Invalid? Compare it to the valid ones. Having distance. 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 So we're comparing the received code word to the valid code words. Distance. The minimum Hamming distance is 2, but there is no unique minimum. That is, there are 2 valid code words which are equal distance to the received code word. In this case, so when we saw it was invalid, we detected the error. That was successful. But in this case, we've received a code word. We think it's either what was transmitted is this code word or this one, because what's received is closest to these 2. So the receiver thinks either of these was transmitted, but we don't know which one. We'll not guess. We have there's no equal probability from the receiver's perspective that it's either of them. So we do not guess. We cannot correct the error. We don't try to correct. In that case, we would need some other mechanism to correct, like a retransmission.
So we're
not dealing with retransmission right now. We just look at the outcome at the receiver's perspective and assume that something else will try to fix it. We could. If we retransmit just one bit, but we don't necessarily know which was the correct one. We don't know where the error is. So what do you want to do? Retransmit just one bit.
And we just ask the transmitter
which one it was.
By asking only the first bit of the data of the
potentially we could have a scheme that says, give me more information to tell me what the correct one was. You need more than one bit, because in fact we need a bit to represent any of the 4 values. We need at least 2, because the transmitter would need to know which. Has to say the correct one was number 2 in that case. But that's more complex, and in fact there are some problems with that. We'll look at retransmission after the midterm. At this stage we just say the receiver knows there's an error, but does not try to fix it, or cannot fix it with the information that it has. error detected but not corrected. We've got incorrect data, but at least we know. Last quick one. 3-bit errors. Last 3 bits are in error. What happens? The last 3 bits are in error. So if the last 3 bits are in error, what is received? If the last 3 bits are in error, what does the receiver do? Data? It's a valid code word. We have 3 bits in error. It's a valid code word. So the scheme is, if it's valid, simply decode. Assume that that's correct. No errors. So the receiver assumes no errors in this case. There were 3 errors, but the receiver doesn't know that. Assumes the received data is 0, 0. That's an unsuccessful outcome. That's the case where an error has been missed. We don't want that to happen, but it can happen, as we just see. So an error correction scheme, we have the 4 outcomes. No error, everything's received okay. That's what we'd like. If there's an error, then we'd like to detect that error and successfully correct that error. In some cases, we can have an error that is detected, but we know that we cannot correct it. That's okay. We'd prefer this, but this is okay as well. As if we cannot correct, then at least we can detect. The thing we don't want is to miss errors. That there are errors, and we don't know about that. So we'd like to choose an algorithm, an error correction algorithm, that maximizes error correction and error detection and minimizes the chance that we miss errors.
And the third possibility, we not concerned about the mechanism of data. Any mechanism?
No, how to correct it, we just say we receive data, it's incorrect. We rely on something else to fix it for us later.
Or maybe use another mechanism?
Yep.
Okay.
Yep. So this is just one error correction scheme. There are others. This is reasonably simple. Think about, and we'll discuss tomorrow, but think about how could you improve this scheme? How could you improve the chance that you can detect and correct errors, and so improve our error correction capability and improve our error detection capability? What would you do to change this? So we'll finish there. Any questions? We've still got a minute or two. We'll talk about the exam and we'll have a quiz tomorrow. Any quick questions on this topic?
The quiz include this topic or not?
No.
Or the quiz include chapter?
Quiz, signal encoding techniques, transmission media. Not this topic.